All right, let's bring it back and let's consider the following problem here, where we're actually finding a limit of this function e to the x minus 1 divided by x. We're finding the limit of that function as x approaches 0. Well, we know that when we're finding limits, typically we initially start by trying what's called direct substitution. That is, plugging in the value that x is approaching into the function itself to see if it gives us a sense of what the limit of this function is. And if I were to find to the x minus 1, if I were to find the limit of that as x approaches 0, we would see that, well, e to the 0 minus 1, this gives us 1 minus 1, which is 0 here. Well, that by itself is not a problem. But if we look at the limit as x approaches 0 in the denominator, if we look at what's going on here in the denominator, we have 0 here. So all of this over 0, and we have 0 over 0. Now, this is what we call indeterminate form. And we talked about this when we first started this course, indeterminate form. Make sure I'm spelling this correctly. All right. And indeterminate form does not mean that this limit doesn't exist. It does not mean that the limit is undefined or that it doesn't exist. It just simply means that the limit of this function cannot be determined in this form, hence the name indeterminate form. So typically, when we have indeterminate form, we see if we can try to rewrite the function in some way. Typically, that involves factoring the numerator and the denominator and seeing if there's a common factor in both that we can try to divide out so that we can rewrite this function into an equivalent limit statement so that this limit, so we actually can evaluate the limit. But looking at what we have here, there's really nothing else that we can do in terms of simplifying or rewriting this function that would allow us to find any other equivalent limit statement. So in comes something that we call L'Hopital's rule. L'Hopital's rule, which we'll write out here. And L'Hopital's rule effectively says the following. If we're finding the limit, given the limit statement, limit as x approaches some value c, right, of f of x over some other function g of x, we would say the following. If f and g are differentiable, if they are differentiable, and I'll just abbreviate this, if they are differentiable, which means by definition that they are also continuous, thereby continuous. So if these functions are differentiable and thereby continuous, and then the next part, f of c and g of c are both either equal to 0 or positive and negative infinity, positive or negative infinity. So if those statements are true, then we can say the following. Then here's the next part. Then the limit as x approaches c of this function, f of x over g of x, is equal to the limit as x approaches c of f prime of x, that is the derivative of the numerator, over the derivative of the denominator. Okay? Now, why is this true? Well, the short answer is that there are a number of different proofs for these. I have written out one of the proofs here. If you scroll down to my notes below, I've given one of the proofs that involves the indeterminate form of 0 over 0. And just as a quick sidebar, let me just go over this because I think it's actually a pretty intuitive and straightforward proof. The proof of this says the following. If we're finding the limit of f over g, and it's established that f of c is equal to 0 and g of c is equal to 0. Again, we're going over the indeterminate form 0 over 0. There's another proof for the infinity over infinity form that's a little bit more rigorous, but you can search it up. And if you have questions about it, feel free to drop a comment below and I can talk more about that. But I just wanted to go over this particular form. So in the form where we're talking about 0 over 0, if f of c and g of c are both equal to 0, f of c and g of c are both equal to 0, therefore, the limits of each of these functions as x approaches c are both 0. Then we can say the following. Well, first off, we're going to rewrite this limit statement so that we're subtracting 0 from the numerator and the denominator. Okay? And again, we're not changing the value of the functions in any way. It then follows that the limit, and they're missing kind of as approaches c here would then be equal to the limit of x approaches c of f of x minus f of c minus g of c, because remember, f of c and g of c are both equal to 0. So we can just replace those zeros with f of c and g of c. And then I can rewrite this limit as the limit, or as the quotient of two separate limits, the limit of f of x minus f of c divided by the limit g of x minus g of c. And this is where you should be getting kind of excited because you probably can see where this is going next. If we multiply the top and the bottom of the fraction by x1 over x minus c, then I can actually rewrite the following. I can actually, and then there's a little bit of a missing step here, which I'll just kind of expand here. This would then be equivalent to the following. The limit as x approaches c of f of x minus f of c over x minus c, all of that over g of x minus g of c over x minus c. And do these look familiar to you? Yeah, this is the alternate definition of the limit, alternate definition of the derivative, g prime of x, sorry about that, g prime of x. So we can then say it's a limit of the derivative of f over the derivative of g. And so it's a pretty quick and easy proof here, but this gives us a sense of why we are able to say it. We are able to say that if both of these functions are differentiable, thereby continuous, and both the limits of the numerator and denominator are each equal to 0, then we can come up with an equivalent limit statement where we're saying this function, or this limit here, is equal to the limit as x approaches c of the derivative of the numerator over the derivative of the denominator. This is what's known as L'Hopital's rule. So, going back to our problem then, if we can then say that L'Hopital's rule does apply here, well, let's make sure. Well, first off, looking at our original problem here, we're going to say the following. We're going to say, let me just going to zoom out here, the limit as x approaches 0 of e to the x minus 1, well, this is indeed equal to 0. And the limit as x approaches 0 of x, well, that's also equal to 0. And since f and g are both differentiable and thereby continuous, then by L'Hopital's rule, which I'll just abbreviate as LH here, by L'Hopital's rule, then the limit as x approaches 0 of e to the x minus 1, so our original limit statement, is equal to this limit of the derivative of e to the x minus 1. Well, what's the derivative of e to the x minus 1? Well, this is just equal to e to the x. The derivative of e to the x is itself. The derivative of 1 is just 0 over the derivative of x, which is just 1. Now, if we try direct substitution here, what is e to the 0 power? Well, that's 1 over 1, which is just equal to 1. Okay? Now, a couple of things that I just want to caution you about here. Notice, in order for us to be able to apply L'Hopital's rule, we need to justify our use of it. That is, we want to show the individual limit statements. We want to show that the limit of the numerator is equal to either 0 or positive or negative infinity, and the limit of the denominator is also either equal to 0 or positive or negative infinity. What I don't want to do, and I'll write this in red because I don't want to do this, I don't want to say that this is equal to 0 over 0. Do not write this. Do not write this. Because this limit may actually exist. We cannot say it's equal to this indeterminate form. We can establish that there is some type of indeterminate form going on. So if you wanted to do something like this, this would be allowed, right? But we don't want to put an equal sign next to our limit statement to say that it's equivalent to this. We're saying that this limit results in an indeterminate form, not that it's equal to 0 over 0, because it's not equal to 0 over 0. This limit actually exists. We just established that it is indeed 1. Okay, so I've summarized that here in these notes when discussing L'Hopital's rule. So just as a reminder, use direct substitution to start. Don't write any type of equality statement of that indeterminate form. Show the individual limits and then apply L'Hopital's rule. Okay, so let's try a couple of quick examples of this, and then I'll give you some time to try to work on a few of these on your own. So first off, let's look at this first problem here. If we take the limit as x approaches infinity this time of x over e to the x, well, we see that this is going to be equal to, the numerator would result, the limit of the numerator is infinity. The limit of the denominator, e to the infinity, well, that can be thought of as infinity. So we can establish that we get the infinity over infinity indeterminate form. But what we don't want to do is say that it's equal. Don't write this. I'm going to clear that out. Okay. Now, let's state the individual limits. The limit as x approaches infinity of x is equal to infinity. And the limit as x approaches infinity of e to the x, well, this is also infinity. Therefore, which is again that those three dots is that therefore statement. By L'Hopital's rule, we can say the limit as x approaches infinity of x over e to the x is equal to the limit as x approaches infinity of the derivative of x, which is 1, over the derivative of e to the x, which is itself. Now, can we find the limit of this statement? Yeah, that denominator is going to approach infinity, and 1 divided by something that gets really, really large is going to be equal to 0. All right, let's try one more example in this video lesson. Let's try this one here. Well, really quickly, if we take the limit as x approaches 0 of e to the x minus 1 plus x. Well, again, e to the 0 is 1 minus 1 plus 0. All of that's equal to 0. And the limit as x approaches 0 of 5x cubed, we're now doing the denominator's limit, well, this also is going to be equal to 0. So therefore, by L'Hopital's rule, since we're stating that this is we're using L'Hopital's rule, we can say that this original limit is equal to this limit here, the limit as x approaches 0, of the derivative of the numerator, which is just e to the x minus 1, over the denominator, which is 15x squared. Okay, so we're saying by L'Hopital's rule, this original limit is now equivalent to this limit here. Now, quickly kind of mentally do direct substitution. What's happening here? We've got indeterminate form again, right? We have 0 over 0 form again. So what we need to do now is we need to apply L'Hopital's rule again and establish those individual limits. So I'm going to do this in a separate color, but we are continuing on the same problem. Now we're going to take the limit as x approaches 0 of e to the x minus 1, which we're seeing, again, this was equal to 0. And the limit as x approaches 0 of 15x squared, this also is equal to 0. So by L'Hopital's rule, again, we can now say that that previous limit, or the original limit now, is equal to the limit of these derivatives, the derivative of the numerator, which is now just e to the x, the derivative of the denominator, which is 30x, okay? And if we try to do e to the 0 power, well, that's going to be 1. The denominator, this is going to be equal to now 1 over 0. Now, in this case, L'Hopital's rule doesn't apply anymore, right? This is not indeterminate anymore. This is just DNE, or that is to say, this limit does not exist. It is not indeterminate anymore. It's not indeterminate because we're not getting 0 over 0 or infinity over infinity. It's simply undefined. The limit here does not exist. So just wanted to highlight that when we have to repeat L'Hopital's rule, we need to show the individual limits a second time, or possibly a third or fourth time. Okay. Hopefully this video has helped kind of establish the conditions for using L'Hopital's rule and also give you kind of a sense of why we're able to use it in the first place.